Hi everyone. Assalamualaikum. Let's start our today's session. And today we're going to look into some of the electrical laws that are in action. We're going to see how some of the theories applied to real life. Okay, so dive into it. And
Don't forget to, all right, that's what I was gonna say. I apologize, Dr. McGee's. I forgot to introduce the topic, brothers and sisters.
ah,
Dr. Abdullah
yes,
McGee is gonna work, of course, in the arena of electronic vehicles, and he's gonna make a move from equations to electronics. The floor is yours again, Doctor.
thank you. Thank you, Doctor. Okay, so this is the second part of our last lecture, and in the last lecture we saw some of the important laws and basics of fundamentals of electrical engineering, in which we covered what are some of the basic electrical circuits, what are voltage, current, and resistance, what are the concepts behind them, and what is Ohm's law. So in today's lecture, we're going to cover the rest of the basic theorems, and we're going to see how some of the real life things are made. So I'll just go ahead and give a quick recap of our last lecture. So if any of you has forgotten it, it would be a good memory fresh. Okay, so moving on. Just give me a second.
Reminding you, brothers and sisters, you are with Atlantic International University, our presenter, Dr. Abdullah Maghiz, in the discipline of electronic vehicles, the drones
Okay.
that both you and I enjoy using.
Yeah.
Everything is
Okay.
coming clear to everybody.
Okay, thank you. So let's move forward. Okay, so we saw that we might have seen in our lives circuits in about a lot of electronics that look like this. There's a green plate and there's a lot of components attached to it. So that's an electronic circuit. So firstly, it is designed on computers and papers, and the design comes from some of the theories. So we need to understand these theories to predict what's the behavior of the circuit is going to be. Is it going to be safe? Is it going to do what we want it to do, and stuff like that? Okay, so how it works is this. So firstly, some human being thinks of an idea, and let's say he said, okay, I want something that turns on an alarm at night, and once the sunlight comes up, so the alarm turns off. Someone would say can say that, or he can say instead of alarm, I want a light to turn on at night, and when the sun comes out, the light automatically turns off. So that's the idea. So an electrical engineer, after hearing this idea, would directly go ahead and from the knowledge of the theory that he has, he would design the basic circuit and use the components that would be doing this job. So here is a small example. Here we would attach an LDR, light dependent resistor, which is a sensor to detect if there is absence of light or excess of light. So this is a light sensor, and then he would attach some basic components to make the circuit do what the idea suggested in the first place. So once the circuit is designed, then he would go ahead and put that circuit in a software and see the output. He would simulate it and he would see, is it going to work? Yeah, okay. So he designed the circuit and he saw the output and yeah, it was working good. So once that was done, so then he would design it physically, he would get a PCB board which looks like something like this. It's a green plate on which electronic components are attached. So, in the exact way that the connections were made in the simulation and the design process, he would connect everything together, and ultimately he would place a good fancy cover on top of it, and that would be the product that you would be using. So from idea to circuit to simulating it and then designing the PCB, and then that PCB is placed in the project. So the rest of the parts are quite straightforward, but this part, the initial part in which he designs the circuit as per the idea of that human being. So designing the circuit is a big deal because you need to know the fundamentals of electrical engineering and the basic concepts behind it. So this was the main well, pathway of designing an electronic product. So moving on. So what is an electric circuit? So electric circuit we saw in the last lecture. It is something that starts with a power source, and there are a lot of different components in it, and it ends with the power source. So if power source is a battery, so one terminal of the battery is connected to a couple of components or many components, and the other terminal of the battery is also connected to these terminals. So that is a complete electrical circuit. So it must have a closed path. So the path is opening from this point. So it is going all the way from here to the other point. So it is overall a closed circuit. So once there's a closed circuit, we can have energy transfer from the battery, from the power source to these individual components. So that is an electrical circuit. Then we saw what are basic electrical quantities. The most famous electrical quantities are these voltage, current, and resistance. So uh, I included these animations to show you that how these things work. In the last lecture, we saw them in greater detail. So voltage is something that pushes the charges that are placed inside a conductor. So movement of charges produces current. Okay, everything is driven by current. Okay, everything, all loads. If you have a small fan or a laptop or a mobile phone or whatever it is that you have, it works by utilizing this current. Okay, everything needs current to move and to do any kind of work or to give you an output. But current needs voltage in the first place, right? So we need voltage indirectly. If there is not enough voltage, the current is not going to move. There is not going to be enough current to drive whatever you want to drive. Okay. So voltage is very important, even though current is the actual thing that is going to drive all the components, but voltage is the one that is going to push that current. And resistance is an inherent property characteristic of all elements, and the job of the resistance is to stop the current. So it slows down. Because of the presence of this resistance, which is indicated by this ohm, because of the presence of this resistance, we need voltage. Because the resistance is this red guy is trying to stop this green guy, which is the current, and this yellow guy voltage is trying to push it forward. So this yellow guy must beat this red guy in the first place. Okay. So in this red guy, there's mentions of this OHM, which is the unit for measuring the resistance, and the AMP is the amperes, amps, which is the measure of units of current, and the voltage is measured in volt. So we have three names mentioned here with their standard SI units, standard international units. Okay, again, this is the detailed definition of what is a voltage. It is in physics, it refers to the work done per unit charge. So how much energy you are consuming on each charge for it to move from one point to another. And we just saw that movement of charges is actually the current, right? And here is the depiction of an animation of a current. So initially, in this figure 1a, you can see that there are a lot of electrons that are free to move in a matter. Okay, so there's a lot of electrons that are free to move, but they're all moving in a random direction. So one is going to the left or on the right, up and down, and all this random chaotic motion is not producing any kind of current. They are moving, they are not producing any kind of current. But if somehow we manage to do something that makes all of these electrons to move in a certain direction, then we would say, okay, there's a flow of current. Now there is a flow of current in this wire. Initially, this was also a metal wire or metal piece or whatever conductor you may think of, but there was no current flowing. The electrons were moving all the way or in any direction, but somehow we did something, and all of these blue dots they turned into a singular direction and they started to move in a certain way, and that produced current. So, what is that something that we need to do to make all of these electrons go into a certain direction? Well, we need to provide voltage. Okay. So if we provide voltage, an electric field is created which pushes all these electrons in a certain direction and their movement starts the current process. So here we can see that all of these electrons, these red dots, are moving in a cylindrical circuit, a cylindrical wire or metal piece, and they're all moving from left to the right side. So we would say, okay, there is a flow of current here. So this flow of current is ultimately going to drive the things. And in the other picture, we also see that, okay, these little blue guys are all moving from the right to the left side. Again, in any direction it can go from left to right or right to left. If all of the electrons are moving in a certain direction, they are going to produce the current in that direction. Anyway, so this was the basic concept. If the electrons are moving in a random direction, there is no current. And if they are moving in a certain direction, okay, yeah, you got yourself some kind of current. And resistance. And the job of the resistance is to resist, right? Resist the flow of current. So we see here in this brown pipe, this brown pipe, that there's a lot of green dots which represent the electrons, and they are all moving from left to right in a great way, all the way to this end. But now we introduce a resistor. Okay, so now during this brown pipe. These electrons are moving, and then suddenly we see some kind of hurdle here. Okay, so you see very small red spots somewhere here between. So what is happening is that there's collisions with this material, and some of the electrons lose their kinetic energy, and this stop the motion. So we are losing some electrons while passing through this resistor. We are losing some electrons, not all of them. So losing those electrons is going to cause us to have a lower magnitude of current. So once there's these electrons come out of this exiting pipe, so now we have lesser amount of electrons available than the ones that went in. So that is the job of the resistor. So it reduces the amount of current by providing resistance, and it is an inherent thing in all of the metals. So no, it is always present there. We sometimes use it, especially, but mostly it is naturally present in materials, the resistance. And then we had this famous Ohm's law that we saw, and that is, well, uh, it is basically the relationship between the voltage, current, and resistance. So voltage is represented by this V symbol, current is represented with this I symbol, and resistance is represented with this R symbol. Okay, so V is equal to I times R. So that is the basic definition of Ohm's law. That the required voltage is the amount of current times the resistance that is available. So that is the amount of voltage that you need for the circuit to work in the first place. Okay, so based on that famous formula that we just saw, we can make this triangle. Okay, and we can introduce different kinds of formulas using this. So if we increase the voltage, we are going to increase the current. If the resistance is same, right? We can see it is mathematical formula, and if we increase the V, we are going to increase the current as well, and that is intuitively right as well. because if there is more energy available to do work on the charges, so more charges are going to move in a certain direction. If more charges are moving, then that's going to increase the magnitude of current, given that the resistance is same. And that is what we see in this mathematical formula as well. And if we increase the resistance, so intuitively we would say, okay, so now we have more resistance, which means that now more of the charges are going to be disturbed by its inherent property of materials. So if more electrons are going to be disturbed, that means we're going to have a low magnitude of current available. So yes, indeed, it does reduce the current. So increasing the resistance does reduce this current. And we can design different kinds of circuits and their behaviors based on this of these intuitions. Okay, so here's the basic circuit of how an Ohm law is being utilized in a real life application. So we got ourselves a battery, a power source, and we have a small light, an LED, light emitting diode. Okay, so we provide electricity using this battery, and this light should turn on. So we got ourselves here a resistor as well because the amount of charge available in this battery is a lot in comparison to the requirement that this LED requires. Okay, so we here in this application we need the resistance. Okay. From the initial concepts, you may think that well, we got this resistance, but we don't want it. But in most of the applications, we do want it. And if the natural resistance of the material is not good enough, we make our own resistors and we put them there because sometimes we just don't need a lot of current. We need to control the current. We need some things that work on very, very low amperes, very low amount of current. And the battery, it has a lot of current, and this resistor is going to do that work. So here is the circuit in real life, and here is the circuit with symbols from the design perspective. So this big horizontal line along with this small horizontal line, these two indicates a power source. Okay, so this symbol is represents some kind of a power source, a battery or a grid station or any kind of power source. And these zigzag lines represent the symbol of a resistor. So it looks like this in real life, but during the design process, it looks like this zigzag circle. And then we have this symbol with an inverted triangle and the horizontal line that represents the LG, the light emitting diode. Okay, so this is how it looks in from the design perspective, and this is how it would look in real life. So then we saw that a lot of things are that we use, a lot of appliances that we use have these power ratings on them. So power is basically the measure of how much work we are doing, how much voltage we are providing, and how much current is being produced. So it is basically the measure of voltage times the current. Okay, and then we can use the Ohm's law, V is equals to IR, to substitute the value of this voltage. Instead of it, we can put IR, and this IR with this I makes this I square R. So we can have different formulas derived from this basic power calculation, which is the voltage times the current. So P is equal to VI is the basic calculating formula for this power. So this was pretty much it about last lecture, and now we're going to see some of the advanced concepts. We'll see only few to give you an idea, and we'll see how these concepts are being used in real life products, so that you would have an overall idea of how these things work. So we have something called Kirchhoff's law. So Kirchhoff was a guy who, well, noticed some things in electricity, and he proposed a few things and then tested them, and well, they become the laws based on his names. So he introduced Kirchhoff's current law and Kirchhoff's voltage law. Okay, so they are based on conservation laws, conservation of energy and stuff like that. So let's see what these laws are. Okay, so what Kirchhoff's current law says is that if we have a node, which is a point somewhere in the circuit, if we have a node, the overall, let's say this red dot that I'm pointing right now is that node. So overall, all currents entering at that node would be equal to all currents leaving from that node. So there are no losses and there's no sudden absorption of energy from the circuit, and there's no sudden induction of energy from outer space to our circuit, but instead we have a simple thing that looks, we can see in the rivers as well. So if we say, okay, we have this point A as a node, so all of the water coming from the river to this point A and is being distributed to these little streamlines is going to be equal. So the input water at this point A will be equal to the water at point B plus water at point C plus water at point D. So if we choose a certain point in a circuit, all of the energy that is going towards it, I would say the current that is going towards it is going to be equal to all of the current that is coming out of it and is being distributed to different parts of the circuit. Okay, so basically, technically, the definition would be sum of currents at a node is equal to zero because left hand side equal to right hand side indicates that if we have left hand side minus or plus the right hand side, it is going to turn out to be zero. So if I have 10 liters of water at point A entering, and I have 2 liters of water at point B, 2 liters of water at point D, and 6 liters of water at point C. So 10 equal to 2 plus 2 plus 6. That would be 10 equal to 10. And if we have a sum at this node, so that would be 10 plus minus 10 because the direction is opposite. So that would be sum of currents at this node are always zero. So in a parallel circuit, the total current flowing through the circuit is divided among any parallel branches as indicated by this analogy. Okay, so this is an example of a circuit that is using this Kirchhoff's law. So we have a battery here and we have different resistors, any kind of load. We have maybe a bulb or a mobile phone or a laptop or any kind of thing. So the current is entering at at this node, which is the IT stands for the total current, T for total. So we have this IT entering, and from this node, we can see that we have I1 leaving out, I2 leaving out, and I3 leaving out. So using the Kirchhoff's current law, we can derive this formula that IT is equal to I1 plus I2 plus I3 because the current entering must be equal to the current leaving. So at this point, the entering current is only 1 IT, and the leaving currents are 3 I1, I2, and I3. So they are both equal to each other. So that is how we can see what is behavior of current in all different parts of the circuit. So that's pretty much it about the Kirchhoff's current law. The short form is KCL. Then we have something called Kirchhoff's voltage law. So he proposed two things regarding the current and the voltage. So the second part is now KVL, the Kirchhoff's voltage law. So what he said in this voltage law was that the sum of all voltages drop around the loop, the sum of all voltage drops around the loop is equal to zero. Okay, so we have these four resistors in a circuit. Okay, so some voltage is being applied to this resistor, some other kind of voltage is being applied to this resistor, and this and that. So we understand that applying voltage means that we are providing it energy from some kind of battery or a power source. So the current flows through this thing, right? So what I would say in easy language would be, so if I am applying some amount of energy here, some here, some here, some here, and all of these things are connected to each other, if I sum the overall energy, the total sum is going to be zero. Okay? So that means that if I have a battery source attached, and it would mean that the amount of energy coming out of the battery is equal to the amount of energy that is distributed in each of the components that are in that circuit. Okay. So here we would see that the voltage that is applied to this R, which is connected between this point A and B, would be voltage AB, VAB. Similarly, for the voltage that is applied to this resistor that is connected between the point B and C would be VBC. And then between C and D would be VCD, and then between D and A, this resistor, that would be VDA. The sum of all these voltages is going to be zero. So if we draw a loop and everything is connected to each other, we will see that the sum of all voltages, the sum of all voltages, right? So that is going to be zero. That is the conservation of energy as well, if you think about it. So, uh, well, this is another example of Kirchhoff's voltage law in a practical meaning. So voltage drops across any kind of element that is attached to it. For example, in power supply that we normally use, power supply is anything that converts from electricity from AC electricity that comes into our households to a DC circuit that is basically used by a lot of different electronic components, including our mobile phones and a lot of different things. So Kirchhoff's voltage law says that in a series circuit, the total voltage supplied by the source must be equal to the voltage used by all of the loads in that path. Okay, so here's an analogy of how Kirchhoff's voltage law is supposed to work. Is that uh, if we have a potential energy at a certain height and uh, we move downwards, so that potential energy is converted to kinetic energy. It's the same amount of energy is being converted to different kind of energy, but the amount of utilization remains the same. The amount that is converted from the potential to this kinetic energy is going to be exactly the same because now it's from instead of the gravitational pull, it is moving in speed, a higher velocity. So if we have a point in a circuit and we have a power source attached to it, then the energy that is being supplied by that power source is going to be equal to all of the loads that are connected to the energy that is being provided by the power source is going to be equal to all of the energies that are distributed among the different power loads, right? So that is the basic meaning of the KVL, the Kirchhoff's voltage law. Okay, so we saw this KVL and KCL, which is a very famous thing in electrical engineering. So this is one of the most famous laws, Ohm's law and Kirchhoff's law. Then we have another very, very important concept in electrical engineering. That is the series and parallel concept. So uh, we can attach things in series and we can attach things in parallel. Okay. So what is the series and parallel? Well, it's a combination of how you attach things in different parts of the circuit. And let's see what is the series circuit. So in series circuit, we can have like a power source and we can attach a light bulb to it. And then we would attach, we can, if now we want to attach another bulb to this circuit. Now we have to think about it, whether we want to attach the second bulb in a series combination or in a parallel combination. Both have their own pros and cons, right? So we would think what we want to do in the first place. Okay, I say, okay, what I want is to provide same current to this bulb A and same amount of current to this bulb B. So I want both of them to glow equally brightly. If I want that, then I would connect them in series because in series circuit, the current remains the same. No matter how many things you attach in a series circuit, the overall current that flows through the series circuit remains the same. So once the current through all these circuits remains the same, then definitely all of them are going to glow in the glow with the same brightness. So the voltages add up and the current remains the same. The voltages are distributed among individual bulbs, but the current overall remains same in that circuit. So there is this concept of series. All of the things are connected to each other, and and they all uh, glow perfectly in the same with the same brightness. But the problem with this series circuit is this: if one of the components is faulty or you detach it, the whole circuit goes off. The whole circuit goes off because when we remove this third bulb as shown in this animation, when we remove this, so the circuit is now open. So the left hand side of this bulb is not connected to the right hand side of this circuit. So there is no flow of current through the air, right? So in a series circuit, if one thing goes off or something happens to it or you remove it, the whole circuit blows off. It does not work. It does not blow off, but it does not turn on because it's an open circuit now. And we saw that for a circuit to work, we need it to be a closed circuit. So we solve this problem with parallel circuit. In parallel circuit, if one component is faulty or you take it off, the remaining things will keep on working. But in series circuit, everything glows equally because the amount of current is same. But in parallel circuit, the amount of current is distributed. It is divided as per the requirement. So we won't expect all the valves to work same, exactly the same. But in parallel circuit, instead of current being the same in each component, we have voltage, applied voltage that is same in all of the circuits. So this is how a parallel circuit would look like. So we have a bulb that is directly connected to the power source. Okay, so this terminal is connected to this power negative terminal of the battery, and this terminal is connected to the positive terminal of the battery. And then we have the second bulb, which is again directly connected to this power source. And then we have the third, which is again directly connected to this power source. Okay, so that is a parallel circuit. Uh, so here the currents are distributed and added. So some amount of current is going to pass through this bulb, and we're not sure how much current is going to pass through the second and third bulb because it's not going to be same. But here we know that all of these three bulbs have equal voltages. So if we remove one of the bulbs, so the current would pass through the other two, right? So if there's one thing that is faulty or damaged, the circuit would keep on running. That's the advantage of a parallel circuit. So sometimes we need to use the series circuit, and sometimes we need to use the parallel circuits. So now these are the two basic combinations that make up a whole lot of complex circuits, right? So, series work versus parallel. Well, we have reliability trade-offs because one is current control and the other is voltage control. So, in a series circuit, both things are connected like next to each other, and if one thing goes off, the whole circuit goes off. But the overall current that is flowing through this whole circuit remains the same. And then we have this parallel circuit. So, if one thing goes off, it keeps on running. That is an advantage that we can expect from him, right? So then, okay, so then we have these complex things called the network theorems. So basically, these are nine theorems. So the first is the superposition theorem. Then we have the Thevenin's theorem. Then we have the Norton's theorem. Then we have the reciprocity theorem. Then we have the Millman's theorem, the compensation, the substitution, the intelligence, the maximum power transfer. So these are the nine theorems that basically govern the most complex circuits that we see in a lot of complex things. And we saw some of the basic fundamental laws of electrical engineering, which were the Ohm's laws and the Kirchhoff's laws. So those were the laws, and these are theorems. So these are the network theorems. We can design a lot of complex circuits that do a lot of things, and all of these designs comes from these theorems. So I will show you only three of them right now, and you would have an understanding of, yeah, okay. So there are some rules and regulations of how these things are working, and based on those rules and regulations we can design a lot of complex things. So let's see one of these theorems. Let's go ahead and see the superposition theorem. So what does this superposition theorem says, and when is it used? So let's say we have a lot of different loads attached to a circuit, which means in real life is this that maybe yeah, okay, we have uh, we have a laptop, we have a mobile phone, we have a bulb, we have some other kind of device all are attached, and there are two or three batteries attached to it as well. So we have multiple power sources and we have multiple loads that are going to use energy from each of them. Okay, so this is shown by this circuit here. So we have one power source here. This is the voltage power source. And then we have this current power source and then this current power source. So we have three sources and we have three loads. So, what superposition theorem says is that you can analyze one source at a time. So, one source at a time is going to get you to evaluate, do the analysis of each element, one source at a time. So, I can use this voltage source and I can just use the superposition theorem to replace this source with something else and this source with something else. So I'm going to replace all the power sources with something that I can use from the superposition theorem, and I can now have a simplified circuit. Now, this simplified circuit is easier to perform the analysis. And now, after doing the analysis, I know exactly what is going to happen with each element. Then we have this Thevenin's theorem. So Thevenin theorem says that if we have a big, huge circuit with maybe 1,000 elements attached to it, right? Maybe 1,000 elements attached to it, something like this. Okay, so we have this IC and this resistor and then another IC and a capacitor and a lot of different components. It's a very huge, complex circuit. Now, I am, due to whatsoever reason, I'm interested in this specific element. Okay, I want to see you how much energy is this element consuming. I am interested in that. So now I can use the Thevenin's theorem. What it says is that you have a whole huge amount of complex networks. You can replace all of that network with a single load and a power source. A single load and a power source. So I can have the load that I'm interested in, and I can replace the rest of the circuit with something that says, okay, the rest part of the world in this circuit, in this circuit, is using this much power and has this much load capacity. Okay, so it simplifies the load analysis. If you want to do the load analysis and do the rest of the design circuit, it simplifies them. So it converts the complex network into a very small, simple thing so that you can work on that specific thing that you wanted to. Norton theorem does the same as well. Well, it does the same as well. It is the dual theorem of Thevenin. It also again converts the whole complex circuit into a single element, but instead of representing it with the voltage source, it represents it with a current source. Why theorem? Because They we use them to have faster designs and easier debugging because debugging is the most important thing in electrical engineering design. Because we can design the circuits, and if one of the component is faulty or something happens to it, we have a huge circuit with very small components, and we don't know how they're going to work. So we need to have these theorems so that we can do some kind of analysis and do the debugging in a huge complex network. Okay. So that was pretty much it to give you an idea about how theorems work. And now we can see some of the basic components and how they look in real life. So resistor is, well, they resist the current, flow of current. They look like something like this. Then we have the capacitors, they store the charge. They look like this. Then we have inductors, they store the, electrical energy. They look like this. Then we have transformers, which are some small transformers, high frequency transformers as well. They look like this. Then we have fuses. Well, if there's they limit the current as well. If we pass too much current, they will break apart and they will not, they will stop the damage that is going to happen. And then we have different other kinds of basic components as well. So resistor is basically a component that has a special kind of high resistance wire uh, wounded around it. So it has some specific value of resistance. Then we have capacitors. Well, it is again two metal plates with some kind of insulator between them. So the job of capacitors is to store charge. So it acts like an instantaneous battery. So it gives you a certain spike of charge, but instantaneously. It does not store a lot of charge for a longer time. Inductors are something that, well, it is just a piece of wire that is wounded around something, and it stores energy in the form of magnetic fields. Okay, so then, firstly, if someone tells us to do something, we select basic components that look like these schematics, and once the schematic is done, we go for this detailed circuit diagram. So the actual symbols look pretty good, but the electronic symbols there look quite complex, and but we design them and we do the analysis so that every component gets the required amount of current so it needs to work on. After the circuits are done, we simulate everything in the softwares, which look like something like this. And the simulation software, uh, Spice is one of the similar simulation softwares. Proteus is another one. MATLAB is another one software. So we have different kinds of softwares as well. And then after the simulations are done, then we go ahead and before manufacturing the actual circuit, we see the components and we see, okay, what is the temperature range, what is the tolerance, what is the availability? Can we get them in our local area? Is this component available? Is this component going to work in the place that I want it to work? So maybe I want designing a product that is going to work in a very sunny desert area, so the temperature may go up to 100 degrees or 150 degrees, and I have to select a component that can bear that temperature. So then I have to see what is the tolerance of this component, how long will it bear if it crosses limit, then the availability of that component. So we go after selecting the good amount of components, then we go ahead and we get these PCBs ready, and behind it all these electrical circuits connections. So all these wires are the connections that connect each and everything with everything, right? So we purchase the components and we put them here and we just plug them together using this PCBs, printed circuit board, right? So, well, why do we need the PCBs? Because we don't want these electrical wires to like move around or get disconnected. So the PCBs will increase the reliability and compactness, and it is required for the manufacturing companies. Then we attached heat sinks, the power dissipation entities. These are the heat sinks. So these are just metal wires. If something gets heated up, we want it to cool down. So we attach these metal, they absorb the extra heat. So once all of this is done, the circuit looks like this, and then we put a fancy case over it. So this fancy case has Ohm's law, the Kirchhoff's voltage law, plus the Kirchhoff's current law, along with those rectifying and filtering elements that we just saw, that those were the capacitors and inductors and the rest of the stuff. All of these things are inside this power supply that you may use in different kinds of things. Then we have this, maybe you have seen something, some kind of drivers that turn on LEDs and stuff like that. So behind them is a lot of electronic components and the same amount of theories. So then we have these sensors. Again, they have the same things, a lot of circuits involved. So we use these laws to measure voltage and current, the KCLs and KVLs. So these laws are practical tools. They bridge the theory along with these hardwares. So if we see how the future direction is going to move, we can see that we need high-speed designs with for electronics. And that's pretty much it about today's lecture. And now we can move into the question answer session. So thank you, everyone. Okay, so I think our host, Dr. Valentin, has lost control over the session. So I can go ahead and ask the rest of the questions from the participants. So let's start with Sissy Jules. Please, sir, you can go ahead and state your question. Sissy Jules, are you available? Okay, so we are in the answer session. Please raise your hands, or you can just write your question in the chat box as well. I will read it from there. Okay, again, we're waiting for the question answer session. So if any one of you is interested in asking any kind of questions from today's lecture, we can start now. So, Cissy Jules, you have your hand raised. So if you want to ask your question, please go ahead, unmute your mic and ask the question. Cissy Jules, are you available? Okay, so if there if you want to ask question at any point, you can just raise your hand and we'll ask that. But from today's lecture, I will give you a small assignment. I have sent a small example question in the chat box. I urge everyone to please solve this example that that utilizes the principle that we studied today. So this question states that there is a circuit node which has 8 amperes of current that is entering, and two branch currents are leaving the node are 3 amperes and 2 amperes. So if there is a third node, what amount of current would be passing through that? So you can apply the Kirchhoff's current law that we studied today to determine this answer. So I want everyone to please try to solve this. It's pretty simple as well, and it does utilize today's concept that we studied. So I hope everyone is working on this example. After a minute, I will explain the solution. I hope everyone is doing it. And if at any point you want to ask any questions, you can just raise your hands and ask the question. Or you can just state your question in the chat box as well. Okay, so I'm going to provide the solution for this example. So we saw that using the Kirchhoff's current law, it says that we have a node and the amount of current entering would be equal to the amount of current leaving. So the amount of current entering is 8 amperes, right? 8. And the amount of current leaving is 3 amperes and 2 amperes, and we don't know the third one. So we have entry of 8 amperes and leaving of 3 plus 2, which is 5 amperes. And still there is something left. That is the 3 more amperes. So 5 plus 3 would be 8 amperes. So 8 amperes entering would be 8 amperes leaving. So the third outgoing current must be 3 amperes because Kirchhoff's current law says that amount of current entering is equal to the amount of current leaving. So the answer is 3 amperes. Okay. So I'm going to give you another example for you to solve that is going to utilize the concepts that we used in our today's session. So the second question is this: a closed loop circuit contains a 12-volt battery, and it has two resistors. It has two resistors with voltage drops 5 volts and 4 volts. 5 volts and 4 volts. Find the voltage across the third element. So we're talking about the current. So this uses the Kirchhoff's voltage law, KVL. So we have a battery of 12 volts and we have two resistors which are utilizing 5 volts and 4 volts. Now there is something that is being dropped across the third resistor. We need to find it out. I'll give you a minute to, to solve this and then provide the solution. Again, I'm stating if any of you wants to ask the question at any point, you can go ahead and ask the questions. Raise your hands. Sissy Jules, if you are available, you can ask your question. If any of you wants to ask a question, he can write that question in the chat box as well. I'll read it from there and give you an answer. Uh, Dr. Walchin, I think I have made you the host again, if I'm not wrong. Can you try to see that if you got your control back?
Yeah, you're correct, that my gaze. I apologize, ladies and gentlemen. Uh, uh, I am so sorry for what happened It's a mistake that I made myself at the very beginning, admitting you, Dr. McGee's, as a host instead of making you a co-host. So
I made that mistake right now.
as a result of that, I have lost entire control. I could not admit new people who were knocking at the door and so forth and so on. I very deeply, from my heart, to you, Dr. McGee's, and to everybody else, I apologize. But as we have a little time left, let me now allow Cece
Hello,
Jules
hello,
Haba
hello,
to
hello.
ask his question. Go ahead, Cece.
Okay, finally. Okay. Okay, my question is based on the Kirchhoff voltage law, could you please explain and differentiate how to calculate the total current in a parallel and serial circuit? Can a PCB means a printer circuit board, combine both parallel and circuit, parallel and serial current circuit, and how to differentiate the PCB according to the type of circuit? Thank you.
Okay, so the PCBs can have on itself parallel circuits or series circuit or any kind of circuit that is not even parallel or series. It can have anything printed on it because wires connecting each other and the physical connection of components. So we can have any kind of circuit attached to a PCB. So if we want to see uh, the differentiation between the KCL and KVL, Kirchhoff's current law and voltage law, it is this that at any node, the amount of current entering is equal to the amount of current leaving. So that is the Kirchhoff's current law. And if we see about the voltage, so that is the amount of voltage that is being provided by the power source is equal to the amount of voltages that is being used by the individual components. So there's no some specific series and parallel circuit because there's a lot of complex circuits as well that are sometimes series, they're sometimes parallel, and sometimes neither of them. So we can't see PCB and state that it's a series or parallel circuit because it may have thousands of series circuits and thousands of parallel circuits on a very small piece of chip, and thousands of circuits that are not even series or parallel. So it's a concept which is utilized in parts, in very small parts of that PCB, but we can't define the whole entire printed circuit board using those tags. Right?
Thank you for your response to Cece Jules Haba's question, Dr. McGee's. Once again, after I admitted uh, many people, many participants who were at the waiting room, waiting indeed. Of course, these folks missed the most important segment of today's class. When we deal with technology, brothers and sisters, we are exposed to mistakes, glitches, and issues that may come up anytime. I lost control over the session at the very beginning after I admitted our wonderful presenter, Dr. Abdullah McGee's. And ever since, I've been unable to unmute people, to admit all of you who were indeed waiting. And please, I am begging you again to forget me. It is a mistake that was made at the very, very beginning. And as a result of that mistake, the whole session was spoiled. I could not admit anybody. I could not unmute, for example, Cece Jules Haba, who was raising hand. And I was, in the meantime, trying to signal to the presenter that I had lost control over the session, which is the reason we had to experiment with this whole ordeal. On behalf of the entire Atlantic International University, I apologize again to each and every one of you. But remember, Atlantic International University loves you. We all have you in our hearts. And if things happen that way on this Tuesday, it is maybe an act of God against which we were powerless completely. But no matter what, I hope you accept my apology, brothers and sisters, as we're going back to Dr. Abdullah Magiz for some kind of summary and a conclusion to this session. But just before that, if you allow me, Dr. Magee, Jima Musa Bali is raising hand. I hope you have a question, Jima, not a comment. I already apologize for what happened, but go ahead if you have a question for Dr. Magiz, Jima, go ahead. Your audio feed is not adequate. We're not getting any audio from you, Jima. Get closer to the microphone or try to go back to the setting. Once again, brothers and sisters, I keep asking for your forgiveness, for your apology. I mean, not for your apology. I am the one who I'm giving you an apology, asking you to accept it. I'm asking for your forgiveness. And we're going back to Dr. Abdullah Magiz, who I hope will forgive also what happened today. But a quick summary and a conclusion, Dr. Magiz, please.
Okay, so thank you. I apologize as well. I was unable to understand. I didn't know that I needed to give back the control. So I tried to ask the question, but didn't understand that they couldn't unmute themselves. So in today's lecture, what we studied was we saw three basic laws that were the Ohm's law, the Kirchhoff's current law, the Kirchhoff's voltage law. We saw three laws, and we saw there are a lot of theorems, and we saw two to three theorems. So we understood that these laws and theorems are behind very complex circuits, and ultimately these complex circuits are used in everyday products. So I hope this session is a recorded session. So if any of you has missed it, you can again uh, rewatch it, and I'm always available for any question answer. So in our next session, we can have a question answer if you have any confusions.